All right, today in class you looked at the formation of an RCC composite, and we started to work on that through class. So I want to go ahead and walk through the problem for you. So we were looking at the concentration through a porous solid. And so what we're interested in here is the concentration of the acetylene as we look through here and look in the pores themselves. Okay, so we're not worried about the solid part. All right, and the acetylene, as boundary conditions, acetylene is going to be a fixed concentration on both surfaces. And you can see from the sketch that we placed our coordinate system in the center of the film. And so x equals 0 is the center. This surface would be minus delta over 2, and then the right side would be delta over 2. And the reason we put it in the center is that since this surface and this surface will have the same solution, we expect this to have the same environment, I should say, then this solution should be symmetric in this film about the center. And so we'll find that when we use a coordinate system on the symmetry of our problem, it makes our solution much simpler. So that's why we chose to put it here. All right, but you're welcome to put it anywhere you want. You just have to have your sketch, and your solution will just look a little bit differently. Okay, but we're going to go ahead and put it in the center. And the big difference with this problem and what we've done already is that during the process of moving acetylene into this film, we're also going to consume the acetylene in the pores by depositing it onto the solid fiber structure. And the deposition rate, so how fast we consume the acetylene concentration, is going to be given by K times C. All right, C is our concentration, K is a rate in units of per second. All right, so we're going to have an extra term in our mass balance. So let's go ahead and take a look at the mass balance. So now we're going to have a flux in and a flux out of our volume element, but at the same time, whatever the concentration is in this volume element, if we were to multiply that by our rate constant K, that's how much we're going to lose in this volume element as it deposits out. And so when we do our sum, we're now going to have that the volume times dc dt is equal to the influx minus the outflux plus, it's called a generation term in our case, where it's actually negative because we're consuming the concentration. And so now what we do is just have to follow the units. All right, dc dt is a kilogram per volume per time, and then we multiplied by volume. So this whole term is then kilogram per time, so kilogram per second. And so our generation term here, our consumption term, we said this is 1 over second, so this is kilogram, again, per volume per second, and we want kilogram per second. So we'll have to multiply this term also by volume to make it the same kilogram per second as the others. Okay. And then again, the flux times A flux is kilogram per area per time. We multiply by the area so that this term is kilograms per time, kilogram per second. So we just have to make sure that those are all the same. So we've got the same formula that we had before in terms of our mass balance, and now we also lose K times C times V. So that's the number of kilograms of acetylene per second that is deposited out and therefore lost in terms of the concentration in the pores. So that will be the term that we use. All right. And then what we're going to do is we're going to go ahead and divide through by the volume. And then when we do that, we get an equation that starts to look like a differential form here on the right side. And then we'll just recall that the partial differential equation of a function is actually going to be the function at x plus delta x minus the function at x. And so here we actually have the negative of the partial differential equation. Okay, so in terms of my choices, I need a negative one, and then this term just stays the same, and so I'm looking here at D. Okay. So when we divide it through by the volume, the A's are constant, so they were pulled out of this evaluation. Okay. And they canceled. That's why we ended up not having the A in this here. Okay. This won't be true when we do the cylindrical case. All right, so that's our equation. dc dt is minus the derivative of the flux with position minus k times c. Now, as an aside, because one problem we had, we did go ahead and set this equal to 0, and then we just integrate it from this point on. The reason why we can't do that here, and I know some of you tried, is that when we take a look at that equation, and then we'll move our dx around, we're going to have these two integrals. This integral is fine, but this one, notice that c here is not a constant. Say the k we can pull out, but c, the concentration depends on position. In fact, that's what we're trying to find. We're trying to find out what its dependence is. So we can't take this derivative without knowing its dependence. Okay? In other words, kc dx, the integral of that is not kcx. Okay, we can't do this integral. All right, so then we move on to the next step. We're going to take Fick's first law, and we'll go ahead and just put that into our equation, and then we'll go ahead and take this derivative, d being constant, and we'll have a second order equation. We can go ahead and apply our steady state condition, and so we end up with this form here. And then that form that we had looks just like this one, okay? Except in our case we don't have a dc dx term, right? So we have a c term and a second derivative term. We don't have a first derivative term. That's fine. So that just means b is equal to 0 in this general form. C, the coefficient out front of our concentration, is just going to be minus k. And then d, the coefficient out front of the second derivative, is a. Okay? So knowing that, this particular form of the differential equation already has a known solution. And so here's the general solution for this form. So all I need to do, I don't need to integrate. All I need to do is plug in the a, b, and c parameters. Okay, b, again, we said was 0. So I just need to go ahead and plug in the a, which was d, and the c, which was minus k, into this solution here. And this is what I'm going to get out for my solution. Okay, so now what we got to do is find our two coefficients b1 and b2. So what we need then is the boundary conditions. So again, the boundary conditions are going to be that, let's see, we got to take a look again at our coordinate system. It's in the center, so that's minus delta over 2, delta over 2. Right, so that's going to be this one. At delta over 2 and minus delta over 2, our concentration in this problem is fixed. It's fixed by the acetylene environment outside, which we assume is large enough that it's not changing. So this is the boundary condition then that we have. And so we can go ahead and plug that into our general equation. Okay, so let's go ahead and do that. And we're going to get these two equations here. So you can solve these simultaneously for b1 and b2. But if you take a look at these for a second, notice that in this equation the b1 is on the negative term, and in this equation b2 is on the negative term. And so the only way for this to work this way is if b1 is equal to b2. And so just by inspection we come up with b1 is equal to b2, and we can write this then in this form here. So this now is our equation that we got from plugging in our boundary conditions that will allow us then to solve for b1. Okay? And then don't forget our general equation. I'm just reminding you of what that is. So once we solve for B1, we can put this in here. Now, to make things a little simpler, one of the things we can see here is that we've got an e to the x, e to something plus e to the minus something. And hopefully that triggers a memory of a trig identity. I'm not expecting you to remember which one, but if you recognize it is one, then we can simply look it up, right? In Mathematica, I can just say exponential to trig, and it'll tell me it's 2 times the hyperbolic cosine of the power. Okay, in our case, x times the square root of k over d. And so my equation here, due to the boundary conditions, is going to be here. Okay, 2 times the hyperbolic cosine of the stuff in the exponent, and my general equation, governing equation, then also has this same form, and so I'm going to rewrite that one as well as b1 times 2 times the hyperbolic cosine of x times the square root of k over d. All right, so now in this form, we can go ahead and solve for b1. And then taking b1, we can plug it right in here to our governing equation, and we'll get the final solution here. So we've got c now in terms of the boundary fixed value on our problem, and we've got our coordinate x, so c is dependent on x, like we said we expect, and this is all a constant down here. All right, so that is our final form. Now, one little thing I just want to point out, notice here that we had the square root of d times k over d, and then here we end up with square root of k over d. Right, these are the same thing, right? Just notice that if I was to multiply the square root k over d times the square root of d over d, right, it's just 1, then on the bottom I'm going to have d, and then on the top I'm going to have square root of k times d. So this is the same as this, so we just changed over to that. All right, so that's our general solution, and then what we can do is we can go ahead and we can take a look at that a little bit. This is in your lesson file, so you can go ahead and play with that plot, but I'll just show you some general trends here. If we were to pick a thick film, so if we had a very thick composite we were trying to produce, then one of the things that we'll see is that by the time we get into the center of the composite, our concentration is consumed completely. And so the concentration in here is being consumed, it's being deposited, and so by the time I get into the middle, I have no concentration left, and so I'm not getting deposition in the middle. And what this means is that the diffusion of acetylene into the surfaces is too slow to get into the middle, and it gets deposited completely before that happens. So this is a bad situation for any kind of reasonable thickness of this composite, because the center will be porous and the outside edges will be dense, and that's not what you want. You want a nice uniform density throughout this composite. So it could work well for very, very thin films, thin composites, but if we put in real numbers, we'll find this is really thin. It's really not practical to use diffusion in this way. Okay. The idea of what the thickness is really depends on the rate of deposition to the rate of the diffusivity, and so you can see that as those rates change, if I've got a very slow reaction rate, fast diffusivity, then my sample could be thicker. On the other hand, if the ratio of those values is such that the deposition rate is high relative to the diffusivity, then it really makes the situation much worse. Again, for any reasonable numbers, this is not going to be a very good way to do this. So What is really done in practice, because this deposition process is used, is rather than count on diffusion, you blow the acetylene through the porous sample and then deposit it that way. And so that gets around the slow process of diffusion. You just blow the acetylene through. Okay, that is it for this problem. Let me know if you have any questions or additional problems with it.